Hi. Now let's discuss about medical imaging, especially in ultrasound imaging. So ultrasound imaging, or I just use it as US, characterization of US is based on the propagation of sound waves through the tissue. But we are using not just like normal sound we are making, but ultrasound, which means the frequency of the sound is higher than typical audible frequency range. So this ultrasound is based on the propagation of high frequency sound waves through the tissue. And ultrasound imaging, I'll discuss it, can be done very fast. So what that means is it not only gives us a structure, but also changes or dynamic changes of the tissue or structure in real time, which when we say real time is like within the interest of our attention, we can see the changes properly. Unlike the X-rays I discussed and CT before, which uses ionizing radiation, now we are talking about sound waves and ultrasound. So that is do not ionizing radiation. So this is safe so that we can use it for pregnant women. You remember, for pregnant women to see the child inside the belly, and also critically ill patient. And this can be also used for therapy with high-powered focused ultrasound beam, which means ultrasound, the sound wave, we can also increase the intensity and even focus the ultrasound using ultrasound lens to focus, and using that energy of this ultrasound to even ablate stones inside our body, or like therapy. So high-powered focused ultrasound is also being useful. So with a tight control, this in general is pretty safe. And think about how to generate ultrasonic waves. You may consider we only need a kind of a membrane to vibrate in a certain frequency of our interest, like let's say 1 megahertz. Then this membrane vibration, like a speaker with high frequency, that will generate a dense and coarse of these sound waves. So in principle, it's relatively inexpensive. And because of this, there are many applications, and ultrasound is one of the most widely adopted medical imaging technology and inside the clinic. So, for example, in emergency medicine, imaging internal bleeding and localized injuries, which is inside the body, we probably use for ultrasound. However, we also need to understand there are limitations in ultrasonic imaging. So, for example, the first is we are using the sound waves through our body, which is mostly in water. But if there is a cavities in air and the bone conduction is, there's a big differences in sound waves. So ultrasonic imaging is not always the optimal through the bone imaging, such as brain through the skull and the lungs, and because there's air and also rib cages. So there are limitations. And another limitation I can think of is we are using sound wave, and based on the, there could be noise involved. So the resolution usually cannot go below like cellular resolution. So how to generate images using ultrasound? So let me first show you a basic ultrasound is, you can think of, you send a wave which through the tissue, and tissue is composed of different types of organs, especially interfaces, and their property of the sound wave with respect to interaction of sound wave are different from each of these, so that when wave propagates, if they meet an interface with different property, some part of the wave will reflect back, while some part will transmit. We are interested in the waves which is reflected back from the interface. And because in ultrasound, we know roughly the speed of the sound. So when it reflects back, we just measure the time difference, which we call as a time of flight. And then we can back calculate where were the interface location. And this is a pretty simple, and luckily the sound waves are propagating slow enough that we can use our electronics to detect this time difference very accurately. So that's how we generate the ultrasound. So let me give you an example, typical example of fetal imaging with ultrasound. You see, this is when someone has a baby, then this is the first image of the baby by using ultrasonic imaging. You can see the sound waves coming top to bottom and hit this interface and measure it so that we can reconstruct these images. And then how can we generate these sound waves, a pulse of sound waves? And there are various ways, but one typical one is a piezoelectric crystals. As I told you before, piezo is a pressure generate electricity. On the other hand, you give electricity or voltage changes that will generate a different movement of the PGT surface that will generate pressure wave, which is ultrasound frequency right now. So we can also focus ultrasonic imaging by using a concave shape, because these, by making this vibration, we can create that wavefront as a focusing. And also the resonant frequency of this ultrasound is in megahertz range. So when you visit a clinic, you may take a look various different kind of ultrasonic transducers, and you may be able to find their frequency range, usually megahertz. So 1 to 18 megahertz. The range is safe with tissue and not audible to human, because our audible range is about 20 to 20 kilohertz, not this megahertz range. And also important thing you understand is this is a frequency that higher frequency is usually giving higher energy, while that higher energy gives you a better resolution. Our tissue, and in general, tissue responds to higher frequency with a lower penetration. So there's always trade-off. You use higher frequency ultrasonic transducer, you gain a better resolution. However, you may not be able to penetrate deep enough. So for example, if I want to use ultrasound to image my whole gut or like heart, you may have to use a lower frequency. While if you use like 10 megahertz, you may not go very deep inside while you have a better spatial resolution. So how do we detect structure? So basically, it's the same as when we are in the mountain, we say, Yahoo, and that the mountain in front of us will have our sound wave reflected back, and we hear the echo. And based on the time of this echo, we kind of calculate the distance of the mountain in front of us, whether it's closer or far. The principle is exactly the same. The only thing is we are not using sound wave inside the air. We are using ultrasound inside the aqueous medium, inside the body. So echo of sound waves that bounces off at tissue interfaces, we just use this one for detect the structure. And that echo or wave reflection, which return back to the transducer, we measure them, the travel, time by using PGT crystal in reverse. So this is quite interesting that So we use piezo for generating sound, okay? Generating sound, and that sound goes and then hit the interface, and then it reflects back. And during time, when we generate sound, we give a voltage input to piezo to generate this pressure wave, while the reflected pressure now returns back to this transducer, and that PGT having this pressure or generate a tiny voltage difference, and that we sense. So using this as a both actuator and sensor together. So that's why I put it in reverse. If we split the time, then we can use the same piezo crystal for generating ultrasound and detecting the reflected ultrasound. And the B is when we have this 2D structure, if we move this 2D on the side by side and reconcile, we can create even this 3D shape of ultrasound. So now let's get into a little more into this. And so the spatial location of each echo can be determined by the, yes, time of flight. That's the time between the generation of the pulse and then reception of the echo. So let's understand about the speed of ultrasound or speed of sound is assumed usually in tissue as about 1.5 kilometer per second. Remember, our sound wave propagates in air about 330 meters per second. And in fact, if it's in water, it's like almost 4 or 5 times faster inside water. You may remember inside the swimming pool, if you hit the wall and that sound transmission is faster. And likewise, it depends on the structure of the tissue. And if it's bone, much stiffer biological material, the sound wave moves even faster, okay? So the time related to the distance. So think about this as a, like, let's say round trip from here to here. So we send a sound and it goes hit and it back. So the distance is D, and the time between this travel, round trip travel was T. Then we can know length, the speed is the total distance traveled divided by time. Or we are interested in the location D, so the D can be described as the speed times time divided by 2. So the C is actually pulse travel speed, the speed of sound, and D is the distance from the transducer to the structure and to ride round trip. So now let's have a simple calculation. So what's the time required to receive an echo from aorta, assuming the transducer is abutted to the abdominal wall and the aorta is 6 centimeters deep. Let's say we have a transducer, we put this here, and I'm sending the sound to about 6 centimeters below aorta. Then what will be the time? So based on these formula, we can see time will be 2 times distance divided by speed. So abdominal belly, the speed of the sound will be 1.54 kilometer per second. And the distance of D is, let's say, 6 centimeters. Then if you calculate it, you get about 80 microseconds. So in electronics, usually we can detect like nanosecond order, and this tens of microsecond is nothing. It's so easy to detect this microsecond. So that's why we can do a very fast processing and real-time update of our ultrasonic images. Okay, so however, we are discussing only one direction, one line of signals. So forming an ultrasound image with transducer pointed in one direction. And then, so that will give us only one line of tissue structure, but if we can have multiple ways, we can have a 2D structure, or we can kind of rotate this directions, we can have this fan shape of the cross section. So pointing many different directions with the transducer by rotating with a motor back and forth like this. We send the sound wave like this, and sweeping motion resulting in pi wedge shape, okay, built from each line of reflection. Let me show you the shape a little more clearly by various types of ultrasonic transducers. So let's say this is sector, and this line is one line of ultrasound, and second line with different angle, then you can have this fan shape cross section, and which is depicted in here. And there's a linear array. So each of the parts will send a linear ultrasound and detect. And there's a more like curved array, so which shows this example. So which we call as the first as a sector, second as a linear array, and third is a curved array transducers. And that provides different shapes in the ultrasonic field of view. We can notice that ultrasound beams from sector and curved array transducers are diverging as they penetrate deeper into. What they mean is when you go deeper and deeper, the spatial or lateral resolution will be compromised. Okay. So that's why in some cases we use a linear array so that we don't compromise the spatial resolution. And the other thing I mentioned before, that we can sometimes utilize ultrasonic energy for, let's say, ablating kidney stones. So those are very important. Another aspect why it's not imaging, it's more for therapy. So we can use as this transducer shape design to make it as a curved concave shape so that we can make it a focused ultrasound. And another interesting modern technology is by using these multiple transducers and controlling the phase or timing of generation of ultrasonic pulse, we can create, let's say, if we give a linear time delay, we can create this steering. So the wave can go this way, the wave can go this way, the wave can go the other way. So that's called phased array steering. And you know, any kind of pattern can be made by generating a proper time delay, so we can make a phased array focusing. So instead of making this transducer shape as it like concave, which is probably more difficult manufacturing, so we can use an arbitrary shape by use of phased array. So this is more advanced version of ultrasonic transducer technology. So let's move a little further. Think of another type of ultrasonic imaging to measure now not just structure, velocity of material or movement inside the tissue. What's moving inside our tissue? For example, blood. So the rate of blood flow or rate of wall motion of the heart, which can be helped by Doppler effect with the sound wave, which you probably know already from your experience in the station of a train. You know that the sound of incoming train versus going away train gives you a different pitch or different way, different frequency of the sound. And that changes in frequency or wavelength of a wave for an observer moving relative to its source can be utilized as a Doppler ultrasonic imaging for functional imaging. So, and another, which I'm not going to discuss it right now, but very interesting advanced ultrasonic imaging techniques involves first example as a photoacoustic tomography. As the name involves, photons generate acoustic source, and we can image with the ultrasound, or so that can create a tomographic imaging. So this is called PAT, which is an emerging technology that allows us for more functional imaging by combining the use of photon and detection as a ultrasound or sound waves. And another example as a advanced one as a functional ultrasonic imaging technique is now because ultrasound is using the sound wave, and the sound wave interaction inside a biological tissue has a mechanical property. So that variations of mechanical property or elasticity can be also measured by functional ultrasound imaging. So based on elastic properties of the tissue, by measuring the change in the structure, which we call strain, when tissue is compressed or stressed. So strain-stress relationship gives the electricity, and we can even probe that elastic property of the tissue. And also, like X-ray, ultrasound also can have a contrast agent, which happen to be a microscopic or nanoscopic level of bubble, which is like 2 to 10 micrometer diameter bubble can become, you can flow them into the bloodstream, and that will generate a high reflection in ultrasound so that we can use it as a contrast agent. And also three-dimensional ultrasonic imaging is adding another axis of rotation of the transducer or arrays of transducer. We can now image in 3D more faster, and that's called 3D ultrasonic imaging. So now I want to just give you an example of advanced ultrasonic 3D, and 4D is 3D plus one more dimension, usually in time. So 3D is usually in space, like 3D structure, and the changes in time, if we collect the data, we call it four-dimensional ultrasonic imaging. So the first 2D traditional ultrasonic imaging, and we can create the three-dimensional ultrasound imaging. This is an interesting example of twins inside a mom's womb, and the differences between 2D, 3D, and 4D is in fact a movie. You can go to YouTube to see how 4D ultrasound looks. And at the last, I want to give you a kind of a recent update for 3D ultrasound imaging, even using a single sensor by use of so-called compressed sensing. So let's see, imaging by line. So we have a multiple of transducer and AD converter, and it can be assigned with a delay so that we can have line by line imaging using array. So let's say this ultrasound gives us a source, gives a sound that will be transmitted field, and then the receptive field will be exactly the mirror image. And those receptive fields will be detected by this multiple ultrasonic transducer, and we can create this ultrasonic images. While there is also plane wave imaging using array, which means we gives the same phase of ultrasound, so unfocused transmission, and these structures will give out the reflection that receive a field, and so that we can have a parallel image reconstruction, which means we can have a total calculation, not line by line. However, you can see here, an issue could be you need a lot of units of AD converter and a lot of piezo sensor. So an idea question is, can we make it even simpler by having only single transducer and single AD converter? And where can we pose more information? By using this, the ultrasonic transducer giving a different kind of compressive coding, which looks like a random, but you know what exactly is. And then it will generate unfocused transmission, and the receive field will be kind of weird, but it contains the information. Now you are collecting it over time, and that can give you a new single sensor imaging. So this is very cool, and I think there are many technological advancements so that which allows us to have a better and faster and high resolution imaging. Okay, so next time we'll discuss about nuclear imaging. Thank you for your attention.